So basically, we have to prove that relation rho on a semigroup S is a congruence if and only if it is both left and right congruence. So we are doing the converse side, that let rho is a both left and right congruence. It means that you take any x comma ts dash comma t dash belongs to rho. So now what we have to prove? We have to prove that SST dash comma TT dash belongs to rho. This is our claim, correct? So now for every what we have, since rho is a left as well as right congruence, so what we have this thing that S comma T belongs to rho. For every A belongs to S, we have SA comma TA, AS comma AT belongs to rho. These two things we have. Now we will apply these. So for any S comma S dash T comma T dash belongs to S, S comma T belongs to rho implies SS dash comma TS dash belongs to rho. Since rho is what? Rho is a right congruence. Similarly, and any S dash comma T dash belongs to rho implies TS dash comma TT dash belongs to rho, since rho is what? Left congruence. So now we apply transitivity T. See, this element is common here. TS dash on second slot, TS dash on first slot. So it is common. So now we apply transitivity T. Since rho is equivalence relation, being equivalence relation, it is a transitive relation. So we can apply. So SS dash comma TT dash belongs to rho. So rho is a congruence. So in this way, this theorem is proved. Proposition 1.5.1 is over. Now once we define a congruence and prove the proposition 1.5.1, we will discuss the quotient semigroup. Quotient semigroup. See, if rho is a congruence on a semigroup S, then S by rho A belongs to S forms a semigroup with respect to forms a semigroup, and this semigroup is called quotient semigroup. Quotient semigroup. Correct? So with respect to binary operation defined as A rho into B rho is equal to AB rho. Correct? A comma B belongs to S here, where rho is a congruence. So if we define operation like this, A rho into B rho is equal to AB rho. First we will check that this operation is well defined. How we check this binary operation well defined? You assume that let A rho is equal to A dash rho and B rho is equal to B dash rho. What is our claim? Claim is what? Claim is that AB rho is equal to A dash B dash rho. This is our claim. So if A rho is equal to A dash rho and B rho is equal to B dash rho implies AB rho is equal to A dash B dash rho, it means that this binary operation is well defined. So we have to prove this. So see, A rho is equal to A dash rho, it re-implies A comma A dash belongs to rho, correct? Similarly, B rho is equal to B dash rho re-implies that B comma B dash belongs to rho, correct? Now, A comma A dash belongs to rho and B comma B dash belongs to rho, it implies what? Since rho is what? Congruence. So A dash comma B dash belongs to rho, since rho is what? Congruence. So it implies and re-implies that A dash rho is equal to B dash rho. What we have to prove? We have to prove that if A rho is equal to B rho, then we have to prove that AB rho is equal to A dash. So A rho is equal to A dash rho, B rho is equal to B dash rho. It means A comma A dash belongs to rho, B comma B dash belongs to rho. It implies that AB into A dash B dash belongs to rho, it implies that AB rho is equal to A dash B dash. That is, binary operation is well defined. Well defined. So we have defined operation like this: A rho into B rho, AB rho. Of course, it will belongs to where? S by rho. Operation is binary, correct? Now what we have to check? We have to check, in order to show that S by rho forms a semigroup with respect to this operation, we have to show that it is associative. Now you take for any A rho, comma B rho, comma C rho belongs to S by rho, A rho into B rho into C rho. It is what? This is what? This will be AB into rho into C rho. Now this is what? AB into C rho, like this. Now you see, we can write AB into C, we can write A into BC. So it is what? Just I am writing here. That is, it is equal to A into BC rho. Now it is A rho into BC into rho. Now it is what? A rho into B rho into C rho. So see, A rho into B rho into C rho is equal to A rho into B rho into C rho. It means what? Associative property satisfied. So S by rho is what? Is semigroup. So it means that this set forms a semigroup, and that such type of semigroups are called quotient semigroup. So always remember when S is a semigroup and rho is a congruence on semigroup S, then S by rho is again a semigroup, and it is called quotient semigroup, and it contains element of type A rho such that A belongs to S. And binary operation is that A rho into B rho is equal to A B rho, correct? Now I want to tell one thing more, that that if we talk about the map S to S by rho, denoted by like this, it is denoted by such type of maps, a natural map from S to S by rho. So, and it is defined by A rho natural is equal to A rho, where A belongs to S, correct? Of course, trivially it is well defined map. So such type of maps are, of course, this map is onto map. For every A rho, you are getting A here. For every A rho, you are getting A here, such that A rho natural is equal to A rho. So clearly, rho natural is onto map, correct? Also, it is homomorphism. Rho natural is homomorphism. For this, for any AB, for any AB belongs to S, you see AB rho natural is what? It will be what? AB rho, and once rho is a congruence, we can write like this: A rho into B rho, and this is what? This is A rho natural into B rho natural. Correct? So in this way, this is, so from S to, I mean to say that the map from semigroup to quotient semigroup will always be a map onto map and homomorphism. Map from semigroup to its quotient semigroup will always be onto homomorphism. That I mean to say. So now we do theorem 1.5.2. Theorem 1.5, 1.5.2, 1.5.3, 1.5.4 are good theorems, and also 1.52 and 5.3 are connected to 1.5.4. So first we will prove theorem 1.5.2. Theorem 1.5.2. What is the theorem? Page number 23. Page number 23. So what is the theorem? Theorem is that S is a semigroup and let rho be a congruence on S. Then S by rho is a semigroup with respect to the operation defined as already defined, and the map rho natural from S to S by S onto S by rho is morphism. So all these things we have proved earlier. And let T be a semigroup and phi from S to T be a morphism, then the relation kernel phi equal to phi or phi inverse is a congruence on S. Oh, this we will prove when there is a monomorphism like this. Okay. So the theorem is that let rho be a congruence on semigroup S then S by rho is semigroup with respect to binary operation defined previously as I have defined earlier, same, and rho natural from S to S by rho is onto homomorphism. So these two things we have proved. We have proved S by rho is a semigroup. We have proved this as a onto homomorphism. So this is proved already. After that, they are saying, now let T be a semigroup, and let phi from S to T be morphism. Morphism is homomorphism. Be morphism. Then the relation kernel phi is equal to phi or phi inverse, that is equal to the set A comma B belongs to S cross S such that A phi is equal to B phi, A phi is equal to B phi is a congruence on S, is a congruence on S. And there is a monomorphism alpha from S by kernel phi to T such that image alpha is equal to image phi, and the diagram in the diagram kernel phi natural commutes. So this is the whole theorem. So see, this relation already we have proved that it is equivalence. Just we have to prove that it is compatible, correct? So we have to prove that kernel phi is a congruence. To prove congruence, we have already proved kernel phi is a equivalence relation in the last lecture. So we have to prove it is compatible. We have to prove this relation is compatible, and we have to prove that there exists monomorphism. Monomorphism means that 1 and homomorphism. And we have to prove image alpha is equal to image phi, and we have to prove that this diagram commutes. Commutes means what? Means that is you have to prove that alpha composition kernel phi natural is equal to phi, isn't it? But basically we are taking elements of the left side of map, so we have to prove basically like this. We have to prove that for every A belongs to S, we have to prove that A kernel phi natural alpha is equal to A phi. We have to prove this. For every A belongs to S, we have to prove A kernel phi natural, because if you are taking element from the left hand side, first kernel phi natural will operate on A, and after that alpha will operate on A, and it should be is equal to what? A phi. Then only we can say that composition of these two maps equal to phi, or we can say that this diagram commutes, correct? So first we have to prove that this is so you take any two elements proof. Take any S comma T comma S dash comma T dash belongs to kernel phi, correct? It implies what? Then what we have? Then S phi is equal to T phi and S dash phi is equal to T dash phi. Now what we have to do? We have to calculate